The 9.2 lesson about molecular bonding is going to be talking about sigma and pi bonds, and kind of would like to get the basics of this first, and that is, if you have a single bond, that is a sigma bond, and if you have a double bond, that's a sigma and a pi, and if you have a triple bond, that's a sigma and 2 pi's. So when you look at a molecule, then you're just going to have to say, okay, well, every single bond here is a sigma. Okay, there's a triple bond that's sigma and 2 pi. So this molecule here has 3 sigmas and 2 pi's, and it's really pretty simple. But we want to have a kind of a deeper understanding, so we're going to go back and look at this more closely. Now, when we have C2H4, that I know if we left you a little while, you could figure out that this would be the structure for the C2H4. It'd have a double bond between the carbons, and single bonds to the hydrogens. And same thing for C2H2. If you play with that a little bit, you're going to figure out there's a triple bond between those two carbons. Now, the other background piece of this is something we talked about, and that was called steric number. And the steric number has to do with how many charge clouds, how many pairs of electrons there are around an atom. And we decided that if we had a steric number of 6, if we saw a structure with steric number of 6, it was octahedral, okay, and that what would happen is that it would have sort of a shape like this. So, we said one up, one down, one left, one right, one coming out of the board, one going back in there. So that's, 90 degrees from everybody. And the hybridization was going to be called D2sp3, or other places we see sp3d2. And again, we mentioned that is controversial, that is not going to be asked on the AP test because other people say that's not even what's happening. The d orbital is not involved, but we're not worried about that. Okay, if the steric number comes out to be 5, it's trigonal bipyramidal. Okay, so that's 3 around the middle, 1 up, 1 down. Okay, there's 90 degrees and 20 degrees for those bond angles, and we say it's trigonal bipyramidal, and the hybridization is DSP3 or SP3D. Okay, now the ones that we will be caring about on this one here is tetrahedral, trigonal planar, and linear. Steric numbers 4, 3, and 2. Okay, if you have a molecule that, like a carbon, let's say methane, that is going to make 4 bonds, those 4 bonds come out at 109.5 degrees from each other, and so they cannot be using the s and the p orbitals, because s and p orbitals, would be circular, and then it would be 3 things that are 90 degrees from each other. We know that it would be like this, and then there's a p orbital this way, p orbital this way, p orbital this way. And so our bonds would be at 90-degree angles, okay, and that's just not what's happening. They're all 109.5. So what we know is going on is the s and the 3p orbitals all blend together and come out as 4 equal sp3 orbitals. And we've already talked about, if steric number is 4, we have this sort of a shape, a tetrahedral shape. You point to the corners of a tetrahedron, and we are saying that is sp3 hybridization. Now for today, we really care about steric number 3 and 2. So for steric number 3, what we have going on is that there is a trigonal planar shape, okay, that they're out at 120 degrees from each other. And what we say is going on is that an S and 2 of the P's have blended together, and now those are going to be 3 new equal sp2 orbitals, and there's also a p orbital, we need that. So we have 3 orbitals getting a chance to move each away from each other in space. They're going to be at 120 degrees. But the picture I really want you to understand is the idea that if there was an orbital out this way, and an orbital coming down, and an orbital behind it, okay, well then there would still be this p orbital straight up and down, okay, this 2-lobed orbital straight up and down. That's this last p orbital right here. Okay, so we'd have sp2, 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 and there would be a p orbital. And we're going to need that p orbital to make double bonds. Okay, and also we're going to use that in resonance. Now when steric number is 2, okay, steric number is 2, we know that we have a blob, this way, a lobe this way, and we have a lobe this way. Okay, so 2 sp2 orbitals. We're saying that, an s and a p, that they blend together, and we get 2 new sp orbitals. And when that happens, okay, I get blob this way, and I get an orbital out this way, but I also still have my p orbital, okay, straight up and down, and I've got another p orbital that's back and forth. Okay, so I have two p orbitals as well as my two sp orbitals. So again, this is a little confusing when you see it, because you say this is one orbital and this is one orbital. Those are sp orbitals. And this part, that whole thing is one orbital, and this whole thing is one orbital. So there are four orbitals here. Okay, the two purple single orbitals and then the two p orbitals. And we're going to need that for doing a triple bond or two double bonds, and we'll see that in a moment. So back to our Pickguard question. Here we have C2H2, and we look at it, and the first thing we say, well, what kind of hybridization is going on? And it's pretty easy. You look at this. Here's a carbon. It's got one to three bonded atoms, and there are no lone pairs on that carbon. So the steric number is 3. And on the other side, same thing. Okay, 3 bonded atoms, H, H, and a C, and no lone pairs on that carbon. So they both have steric number 3. Now we know steric number 3 is sp2 hybridization. So for this carbon, there is a bond coming out like this, and there's a bond coming out like this, and there's a orbital coming out like this. So these are my 3 sp2 orbitals, and I've tried to draw them so that they are kind of perpendicular to the plane of the board. So this is right in the board, this is coming out at us, and this is kind of going back behind us. And we still have a p orbital, okay, and so this carbon has a p orbital. I'm just going to put a line in just to represent where it is, and that's going to be this pair of electrons. So one pair of electrons is going to be between these two here, okay, and the other pair of electrons is going to be part of this p orbital. Okay, let's get the other carbon. I just did the carbon on the left. Let's do the carbon on the right. And the carbon on the right, here it is, and it is sp3 hybridization, so it's going to be sp2 hybridization. I always say that wrong. sp2. So here's an sp2 coming out toward us, and an sp2 going back a little bit, and an sp2 going this way. So between us, between those two carbons, then there is overlapping orbitals. That's called valence bond theory. Overlapping orbitals where the electrons get to be close to the protons of both of those carbons, and that makes a bond. And because the electrons are right between those two atoms, okay, then we call that a sigma bond. And a sigma is, that funny little symbol there. We have a picture of it here. So there's a sigma, okay, and that's a capital sigma. Sigmas, we use that for summation. Okay, so capital sigma. This is lowercase sigma. Sigma means the electrons spend their time right between those two atoms. Now, this carbon over here also has a p orbital sticking straight up and down. So remember, it's sp2, so that means that it has 1, 2, 3 sp2 orbitals, and it also has this p orbital. So those are the 4 orbitals, and we're using them to make the bonds. Now, this hydrogens, we've got to stick our hydrogens on out here, and those are sharing a pair of electrons, so they are out here, sharing their electrons from their s orbitals. Okay, so that's a sigma bond, and I made that kind of messy. And here's a sigma bond, and here's a hydrogen making a sigma bond, and here's a sigma bond. So each of these little orbitals out here, I'll do it in yellow. Okay, that's a sigma bond, that's a sigma bond, that's a sigma bond, that's a sigma bond. So far we've drawn 5 different sigma bonds. Okay, so all these single bonds are sigma bonds. Then the last thing here is that these p orbitals can blend together, and when they do, they share above and below the plane of the molecule. And when that happens there, that is a place to all of this orange area on top and on bottom together is one big pi bond. These are p orbitals, so we symbolize them with the Greek letter pi. Okay, the s orbitals below we were symbolizing with the Greek letter sigma. Okay, so pi is a bond where the electrons are spending their time above and below these two carbons. Okay, so here's the carbons, and so pi bond is above and below. So this whole big blob of orange counts as one bond. Okay, one pair of electrons. And on our picture over here, that's the two orange, or we're drawing below again. So these are the orange, and that's that pair of electrons. And the other pair of electrons is over here in that sigma. And that's what makes a double bond, a sigma with a pi. Okay, for the other picture, C2H2, here we have, okay, we can see that for each carbon is sp hybrid. Well, if we're doing sp hybrids, and we have an sp, and then we're going to have a p orbital, and we're going to have another p orbital. We have two p orbitals. So I'm going to color code these dots. Okay, I'm going to have one pair shared in one p orbital. I have one pair shared in another p orbital, and then one pair is going to be shared in sigma bond. And the same thing going out for the hydrogens, will be sigma bonds. So let's do the carbon. Carbon on the left, okay, it's got two sp orbitals, and we know that the sps are linear. One goes out this way, one goes out this way. But when that happens, then I also have a p orbital that's going to be up and down. And I can have a p orbital, and I want to draw that at 45. It's supposed to be coming out of the board, so x, y, and z. So my two sps are in the x-axis. Okay, my orangey p orbital is in the y-axis, and the green is z. And I'm going to draw my other carbon while I'm at it. Okay, it's doing the same thing. Here's an sp orbital here, and then there's an sp out this way, and then it has two p orbitals as well. Now, I'm going to put in the hydrogens. So the hydrogen's out here, okay, using its s orbital. So we make a bond here. Here's a hydrogen out here making its s orbital. And those are all going to be sigma. So there's a sigma between the two carbons. There's a sigma between the carbon and the hydrogen, sigma between the carbon and the hydrogen. Now those red and green things, okay, are going to form pi bonds. Okay, so these are going to share here in front. So this is coming out of the board, and also back here, these are shared. So this, again, this big green blob counts as one big pi bond, and that's this one pair of electrons between the two atoms. And at the same time, in the red portion, okay, so this is going straight up, and it will also be down. Okay, a lot of that is blocked by the green. Okay, so they're sharing above and below the plane of the molecule. Okay, let's see if I can kind of get that a little bit nicer. Okay, and I'm going to redo my green here. So the green is out here in front. So that green area is one pi bond, and the red area is one pi bond, and then I have three sigma bonds. So again, what we're saying is that if I have a single bond, then a single bond is a sigma bond, and here's a sigma bond. But if I have a triple bond, there's one sigma, one pair of electrons right between the two atoms, and then I have a pair of electrons that are above and below the molecule, and a pair of electrons in front and back of the molecule. So this is a triple bond, okay, a sigma and two pi's. And that's what that kind of a bond is. Okay, so again, notice what we're doing is we're using these two, okay, in order to make three bonds. So here we have a sp2, 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 and then there's a p orbital straight up and down. And that p orbital is useful for doing that double bond. Okay, for the sp, when we're doing the triple bond, okay, we had our two sp orbitals, and then we had two p orbitals that were available to make a triple bond. Okay, now when we get to nitrate, we have nitrate and benzene to worry about. Let's do nitrate. So if I were doing nitrate, I would say NO3 minus. So I would start off and say, let's give everybody an octet and see if that's the right structure. And if I do that, I say I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. I've used 26 electrons. But if I count up nitrogen, 3 oxygens, and a minus charge, that's 5 plus 18 plus 1, that's 24 electrons. So I don't have 26. So I have to take away a pair. And, so what I'm going to do is take away a pair that only counts for the nitrogen, and take away a pair that only counts for the oxygen, and replace it with a pair that counts for both nitrogen and oxygen. And that gets me down to 24 electrons. So this is a decent structure. The problem is that now I have to say, well, if I did it that way, I could also do it any of the other ways. So my real answer is that there are going to be 3 structures. And each of those 3 structures, I can have a double bonded O this way. I'll do a double bonded O down. And I'll do a double bonded O to the right. And patterns, watching my patterns, that whenever I do a double bond, I get 2 lone pairs. Single bond, I get 3 lone pairs. Okay, 3, 2, 3. And this will be 3 and 3, and this will be 2. And I'll put in my brackets and charge. Okay, and I would put double arrows between each of these. And that's if I said draw the Lewis structure for nitrate, this is what I would really have to draw. All 3 of those structures. Now, we don't think that they are bouncing back and forth. We don't think that that double bond is to the left and then the next moment it's down, the next moment to the right. It's not cycling around. It's just that this way of showing where the electrons are just doesn't work. It's not sophisticated enough to show what's really happening. So that's why we're going to be using our hybrid orbitals to show what's really happening. Now, if I were to ask, what is the steric number of this oxygen? Okay, you would say it's 1, 2, 3, because here's 1 bonded atom in 2 lone pairs. That would be 3. The fact that it's a double bond doesn't matter. How many bonded atoms, lone pairs. And if I ask for the nitrogen, okay, the nitrogen has 1, 2, 3 bonded atoms, no lone pairs on the nitrogen, so that counts as a steric number of 3. Now it turns out that if I look at the other ones, they look like steric number 4, but that's not what's happening. And when we have resonance, then all the atoms that are in the resonance are all sp2. They are all sp2. So we're going to have sp2, 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 and then we're going to end up with one more orbital. That's our p orbital. Okay, we're going to have sp2, sp2, sp2 at 120 degrees, and then we have a p orbital. So let's see if we can draw this nitrate. So I'm going to go down here. Okay, so nitrogen, what I'm going to do is give it nitrogen, and I'm going to do this kind of like I did before, sideways. So 1, 2, and 3. And we're only going to draw one picture, because one picture with these diagrams like here will cover all 3 of those other resonance structures. So we have the 3 sp2s at 120 degrees. And then there's a p orbital sticking up and down. And I'm just going to do that, just to save the place. So when I get down here, here's an oxygen, and it's doing sp2. So sp2, 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 and it has a p orbital up and down. And back here, here's an oxygen doing sp2, 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 and it has a p orbital straight up and down. And finally over here, here's an oxygen going sp2, 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 okay, and it has a p orbital up and down. So you can see what's going to happen is that right between those 2 atoms, we're going to have a sigma bond. And between here, there'll be a sigma bond. And between here, there's going to be a sigma bond. Okay? There's going to be a lone pair in each of these outer orbitals. There's a lone pair of electrons. I'm just going to kind of sloppy draw them in. And then the key thing is all of these, everybody has a p orbital. And all these p orbitals are going to blend together. So it's going to blend together above and below. And also here, oops, that's okay. Okay, and up here in front, these are going to blend together. And they're going to blend together back here. So what I'm going to end up with is a 120 degree, sort of a trigonal planar pi bond. There's another one bond back here. So I call it a propeller-shaped pi bond. Okay, above and below the molecule here. Now that I've kind of obliterated part of my picture, I'm going to go back and put this in. So this lone pair would have been in front of my orbital. I wouldn't have seen it very well. Okay, so there's a big 120 degree, okay, propeller-shaped pi bond above and below the molecule. So all that whole big thing is one big pi. So what that means, if we go back to our picture, is that there is a pair of electrons that spend its time, okay, 100% of the time holding this molecule on, holding it between a bond between each nitrogen and oxygen. And then there's one more pair of electrons that seems like it spends its time, on all the atoms. Okay, it doesn't jump from place to place. It spends all its time here, okay, in above and below, and that helps to hold it together. So we have these sigma bonds, sigma bond here, sigma bond here, sigma bond there. Okay, that's one. And then there's a third of this other pair of electrons that holds it. So these guys have a bond order of 1.33. Okay, got 1/3 bonds holding each of these, making each of these bonds. And that is the nitrate. Okay, now, tucked away here is C2H6. Let's throw it on and get some more room. If I said, okay, C2H6, then if you played with that, you would find out that if we made a hexagon of carbons and made every other one of them a double bond, and then each of these carbons still has one more bond because they can make 4 bonds, we'll put the hydrogens on. And if we did that, we say, okay, well, that was good, except I could have done the same thing, but put in a double bond. So this, I have a single, double, single, double, single, double. And now I'm going to go back and do double, single, double, single, double, single. And with my hydrogens out here. So I get 2 resonance structures for this. Now we can see what's happening. Everybody really has sp2 hybridization. So looking straight down at this, okay, I would say each of these carbons, okay, is doing sp2, so it's going this way, and this way. And this next carbon is doing this way, and this way. This carbon is 1, 2, and 3. This carbon, 1, 2, 3. This carbon is 1, 2, 3. And this carbon is 1, 2, 3. So each one of those is doing sp2 hybridization, and that makes sigma bonds. And then hooking on my hydrogens out here, okay, hydrogens are going to use their s orbitals with the sp, okay, to help make a bond. And then finally, everybody has a p orbital, and that p orbital, okay, I'm going to make it red this time, is going to float above this whole molecule. So each of those p orbitals blend together, blend together, blend together, blend together, okay, and we get one big circular pi bond, but that's going to be above and below this molecule. So I'm going to try to draw this from the side, and so I have a carbon bonding, 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 okay, carbon bonding, 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 okay, carbon. So each of these, I'm trying to draw 3 of my sp2 orbitals, okay, and as it does that, okay, the hydrogens will be out here with their s orbitals, so it's all sigmas, and then above each of these, because they each have a p orbital that has a part above and it has a part below, and the above parts all blend together to get a circular pi bond that floats above this ring of carbons. And then there's one down here that floats below the ring of carbons. And I'm going to go back and put in my carbons now that I've kind of obliterated them. Okay, so I think we'll be able to see that one. I think that looks pretty good. Okay, so that ring of carbons is above and below the plane of the molecules, okay, and that makes it very stable because the electrons are delocalized around there. Okay, so that is hybridization, okay, using hybridization to show what's happening. And for the C6H6, whenever we get a resonance structure, then we know that everybody really is sp2 hybridization, okay, because that means we have an sp2, 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 and we have a p orbital. And those p orbitals can blend together to give a pi bond. So this one big circular pi bond. And again, remember, above and below all counts as the same pi bond. Now, on the back side, on the bottom here, okay, we have this picture. It says key ingredient in sunscreen products. So draw in the lone pairs and the hydrogens. So I made a really big version of that. And on the oxygens, there's going to be lone pairs. Remember, in structural formulas, we don't usually draw those. Okay, and that's kind of important. And just like we did with the benzene ring, there are a bunch of hydrogens. So there's a hydrogen here, and there's a hydrogen here, and we don't draw them in. Okay, and there'd be two hydrogens right here, and then there'd be hydrogens on each of these corners. And I think that's everything. So we say it says draw in the lone pairs. We did that. Okay, determine the hybridization and geometry, bond angle, each of the circled atoms. Okay, we see that's a steric number of 4. And so therefore it's going to be, what's the question? Hybridization and geometry. So 4 we know is 109.5 degrees ideally, and that's going to be sp3 hybridization. If I look at this one here, okay, then that is steric number of 3, 120 degrees, and that's going to be sp2 hybridization. Okay, right there, okay, that's going to be steric number of 3, and that's going to be 120 degrees, and sp2 hybridization. And this guy over here, we can see it's going to be 4 bonds, so Sn equals 4, and that's a 109.5 degrees, and that's going to be sp3 hybridization. Okay, those are the only ones we worry about. Now, there is something called the conjugated system, which is pretty important. The conjugated system means we have single, double, single, double, single, double. Okay, and you can kind of see what's happening here. Here's a single, and here's a double, and there's a single, and there's a double, and a single, and a double, okay, and a single, and there's a single, and there's a double, okay, and all of those together, okay, all these electrons they all have p orbitals, okay, and since they all have p orbitals, okay, I'll kind of draw them, so it'd be a p orbital here and a p orbital. Since all these p orbitals are here, then the electrons could actually flow from atom to atom. And if they do that, then they can actually be, the electrons could all kind of maybe be on one side or all on the other side, and you get slightly different energies, okay, if all the electrons are kind of relaxed or if they're all pushed to one side. And those energy differences are usually right in the UV or the visible range. And that's what, this is a good sunscreen because it absorbs UV because of this conjugated system. And I think there's also you can say there's a conjugated system here. Okay, single, double, single, double, single, double. Okay, and so that's what these benzene rings usually have, that thing. Okay, now it turns out that if you really study this more, something funny happens in here. Okay, so actually this whole system is one big conjugated system, one big pi bond, and that's why it works, it absorbs energy nicely. But, I think just looking at it, you might have just recognized the single doubles just on the two sides. And that's what this guy is, a good UV. Okay, now, really quickly here, there are different kinds of spectroscopy, and you just have to know a couple of things, and this is notes. And one of the things you're supposed to know is that infrared would cause molecular vibration. Okay, so here's NMR spectroscopy, nice stuff. You'll learn about it in college. Don't worry about it now. Okay, IR spectroscopy, and these molecules can bend and stretch and, all this stuff in different ways. And because of that, like I said, this is characteristic for an OH bond in a carboxylic acid. This is this kind of absorption here at this wavelength is at C double bond O's and a CO bond. So, if you have a molecule and you do this to it, you run an infrared energy through it, and it absorbs a characteristic thing. So IR spectroscopy has to do with bonds. Okay, it'll tell you kind of what bonds are there, and that's useful. For UV and visible, okay, we've done this kind of thing when we're doing our colorimetry, and we can find out, that the electrons, we're talking about electrons moving, from the one level to the other, and when they do move from one level to the other, they absorb visible light or in the UV. Okay, and if that's the case, we can tell something about the concentration of these. So we're talking about absorbing in the valence shells. Okay, and the last piece here, X-rays, and that we've learned about that. You can get the deeper electrons go from the 1s, and they can go from the 2s and the 2p and 3s. So we have 2 from the 1s, 2, 6, and 2. We know that this is magnesium, And as you know, X-rays can cause those core electrons to be ejected out. And so those are the three you're supposed to know about. Okay, infrared will make bonds. You can tell what the bonds are doing. And UV and vis, we can excite the valence electrons. And X-rays, we can excite those core electrons. And that's what you need to know for 9.2.